Hello everyone. As I have promised you that I would like to do some lecture videos on me going over this section 4.5 exercise. I mentioned many times in class that this section requires a lot of exercise. You need to have a lot of hands-on experience in working with substitution method. Okay. Substitution method is the first major method of integration, and I think that's the only big technique of integration you learn in calculus 1, which once you go to calculus 2 later on, you will have a lot more technique of integrations. Okay, so from this point, I would like you to not only practice a lot, but at the same time sharpen your intuition. Now, I'm recording this not only for my student in fall 2025 at Santa Monica College and West LA College. I also record this for my future students and students everywhere, of course. Okay, and I hope you can benefit from this lesson here. Okay, let's start with I chose some questions that I want to go over from section 4.5, James Stewart's regular calculus textbook, the 9th edition. Okay, this is from, so these questions are from calculus, the regular edition, calculus 9th edition by James Stewart. And I chose some questions. Now you see that I will go over a lot of problems, but you will see one of the main issue is how do we choose our u to substitute which expression. Okay, which expression to substitute and becomes our u. And then in between later on you will see some more complicated situation where the substitution result in more substitutions. Okay, now in between we will also see the symmetry, integral on symmetric domain. Okay, like opposite domains, but the function is symmetric. Maybe it is an odd function or even function. Okay, and then I will go further into from the integral, then I will go to definite integral. Okay, let me start with question number 6. Okay, we have a friend joining us right now. He is TB, and yes, I asked him to interrupt me anytime he has any question. Okay, let me stop my video. Let's start number 6. Then from number 1 to number 8 in this section, the author wants us to evaluate the integration by making the given substitution. So they tell us the substitution. Now you will see later on the substitution should be predetermined. Now they tell us u equals to 1 plus 1 over x, which is the guy we have inside the square root. And you will see that if we have a square root with 2 terms inside, usually, at least at this level, usually that becomes our u substitution. Okay, so that's our u here. So what is our du? This is u equals to 1 plus x to the negative 1. So du, the differential, will be negative x to the power of negative 2 dx, which we can write as negative 1 over x squared dx. Now notice that the 1 over x squared dx happens to be what we have as part of our du, right? Okay, now so I will do substitution later on, but before that, let's do some modification first. I need to rewrite that 1 over x squared dx. Therefore, notice that this is equals to du, right? So this will be negative du. Okay, so I will replace 1 over x squared dx as negative du. Now continue with this integration. Okay, the square root of the yellow, I purposely do the color coding. I hope that helps you to visualize that. Okay, but of course, when you have your own assignment, your own test, you may not use this color coding, but you see the pattern already. Okay, which one we substitute? This becomes square root of u, and then 1 over x squared dx, the blue portion, becomes our negative du. Okay, now I will rewrite that. Now remember, as I have said many times in my class, and also for future students and students from other class, in math, we actually have a little principle that the next step is shown in the next line. So avoid, unless you know it's not that much different, avoid writing it next to it. I think this one is reasonable, right? Yeah, this one is reasonable, just rewriting it. But try your best not to do that. Write the next step in the next line. It is preferable. And you will see it's actually visually more convenient. You know, so I bring the negative out, u to the square root of u becomes u to the 1/2 du, and then the integral becomes, I copy that negative, u to the 1/2, I increase the exponent by 1, and then multiply this expression by the coefficient, the reciprocal of the exponent. Don't forget plus constant. Now after that, then we substitute our u back to what the u was earlier. The u was 1 plus 1 over x to the power of 3/2. Don't forget plus constant as usual. Okay. It is possible that our textbook or other textbook or your instructor would like you to rewrite that in radical form. So this will be written as negative 2 over 3 square root of 1 plus 1 over x to the power of 3 plus constant. Okay. Of course, you can write the power of 3 outside of the square root instead. Negative 2 over 3 square root of 1 plus 1 over x. Okay, that's the 1 over 1 plus 1 over x to the power of 1/2 is this guy here, and then the power of 3, you make it like this. Okay, let me clean it up so that you can see without the color.
Oh, Thomas, it looks like we have another visitor.
Oh, thank you, thank you. Let me pause it. So that's what happened if we did this. So we have 3 possible ways to answer this. They are equivalent, but of course, it depends on your instructor, who your instructor is. You may want to ask, sir or ma'am, do you want this style or this style or this style? It's supposed to be okay either one, but like our textbook will show you one style and you write another style, you think you're wrong, while actually no, it's just different style of writing. Okay, number 8. Again, they tell us what's the substitution. They say u equals to c minus 1 because the integration respect to z, right? And you notice again that usually if inside the square root or cube root or whatever root, whatever power it is, if you have a group, like in this case c minus 1, usually that's the one we substitute. Okay, so if that's our u, then our dc will be du. However, notice that if our dc equals to du, what happened to that z? Let me color that another way with a purple. Then I need to play from here. Okay, if u equals to c minus 1, then c will be replaced by u plus 1. Okay, that's our substitution. Therefore, this integration becomes integral of u plus 1, u to the 1/2 du. Then, as before, I distribute u to the power of 3/2 plus u to the power of 1/2 du. Then integrate u to the power of 5/2. I multiply by the reciprocal of the exponent, u to the power of 3/2, then multiply by the reciprocal of the exponent. Don't forget plus constant. Now, our textbook have a tendency at this point to replace the u by whatever the substitution is. And that's okay. That's totally fine. In fact, if you ask me, Thomas, is it okay for me to stop here and just substitute right away? To be honest with you, I'll be very happy if you can go this far at this point. But if you are in my Calc 2, I would like you to go a bit further before you do that substitution. Okay, notice that at least we have a common factor 2 and u to the power of 3/2. Okay, in fact, thinking about it further, we have common factor 15, denominator 15. Therefore, if I took 2 over 15 out, I will get 3, and for the u part, it will be 3 to the power of 2 over 2, or 3u, plus u to the 3/2 already out, the 2, exponent 2 already out, denominator 3 already out, I have 5 here. Because in your Calc 2, or of even further differential equation class, if you go that far, then the textbook will want you to go to simplify that this far. Okay, this is 2 over 15. U to the power of 3/2 will be z minus 1 to the power of 3/2. The magic happens inside the parentheses, 3 times z minus 1 plus 5. Notice I can distribute and then combine like terms there. Okay, I skip one step. You think about how do I get the final answer here, 3z plus 2. Okay, you distribute the 3 and then you add with the 5. Okay, so now I hope you see that's actually a lot simpler. Okay, that's for number 8. Let's go on. The next couple questions, the next few questions, we evaluate indefinite integral, but they don't tell us which will be our u. And this is where I want you to start developing your skill in choosing appropriate u. And you will see that most of the time is the grouping. You know, like in this case, number 10 here, okay? I know how to integrate u to the power of 10, right? I know how to integrate this. This is 1 over 11, u to the power of 11 plus constant, right? Okay, if that becomes the u. So let's make it u first. It's like in class, I usually call that the ugly guy, right? If that guy is ugly like Thomas, you substitute Thomas, right? Okay, so du equals to negative 3 dx. Okay, that's our u. But what happened to our dx then? Oh, we have that here. So let's play with that. So our dx then becomes du over negative 3. That's our dx. Now let's do the substitution then. This is integral u to the 10 du over negative 3. Take a look on how I substitute them. It's really just substitution. It's really just substitution. Just make sure you substitute everything such that, I said this in class, I said this again. We substitute from x becomes u. Once you do that u substitution in your new integration, there should not be any x anymore. Some instructors allow that, okay? I don't allow that at this level, okay? Because it may make your computation a lot harder later on, you know. So simplify that, simplify everything here, okay? Simplify everything there. Okay, in future, if you see more complicated situation, then you may have x inside, but so far, even up to pretty far in your Calc 2, I never see that happen. I myself, as your instructor, when I learned this myself in decades ago, my professor himself emphasized that it is not a good habit that after we do u substitution, we still have x in our new integration. It's actually very bad. It's actually very bad. I have seen a lot of my friends, and therefore a lot of students after that, when I teach, actually mess up the integration and get the wrong answer, simply because they have done the substitution partially. Okay, so do it in full like this. So I will factor the negative 1/3 out. So I have that integral u to the 10th du, which actually you can skip this step if you know what is integral of u to the 10th. That's what we get. That's negative 1/33. And then I substitute the u back. 5 minus 3 x to the 11 plus constant. Okay, that's for number 10. Let's see number 14. Number 14, we have integral of secant squared of 2 theta d theta. We know what is the integral of secant squared x dx. That is tangent x, right? So if I can substitute or make this something I know, the 2 theta, then it becomes sine square u, right? Okay, so let's make it our u. U equals to 2 theta, so du equals to 2 d theta. Therefore, d theta later on will be substituted by du over 2. This becomes integral of secant squared u du over 2. That's 1/2. Integral secant squared u is tangent u. Don't forget plus cheese, plus constant, right? Okay, that's 1/2 tangent u, which is 2 theta, plus constant. Okay, number 10 and number 14 have it's the same principle, right? If we know for number 10, if we know integral of u to the 10 du, then it's doable. For number 14, if we know integral of secant squared dx, then we know. Okay, so somehow we kind of like refer to, oh, you know what is the integral that I know how to do? And therefore, I will play with the ugly guy, substitute the ugly guy, such that I only end up with the terms or the integrand that I know how to deal with. Okay, number 16, let's say we have that y squared times this ugly guy, 4 minus y cubed to the power of 2/3. Oh, wow. But hey, you know what? This is partially joking, of course. Like, we need to know how to deal with ugly people. Okay? Because what? This world is a lot of ugly people, like Thomas. Okay? Thomas, you are so self-degrading, huh? Oh, I'm joking, right? Okay? More or less, that's true, though. Like, we need to know how to deal, analyze, and handle ugly situation as well, right? But then it goes back to the principle. The principle is, if this guy or this ugly expression here can be substituted by reversing the chain rule, right? That's basically the principle. Then the situation may be actually very well doable, right? The integration is doable. I did that substitution and notice that y squared dy is a factor of my du, so I will rewrite my du over negative 3 as y squared dy. Okay, so y squared dy later on will be replaced by du over negative 3. It's integral of u to the power of 2/3 du over negative 3. Okay, now that's negative 1/3. I will integrate this at the same time. U to the 2/3, when I add the exponent by 1, I get 5/3 Okay, and then multiply the coefficient by the reciprocal of that new exponent, 3/5, plus constant. If you ever wonder, Thomas, how can you add 2/3 by 1 so fast? It's actually you should be able to do this. You are in Calc 1, right? Should not be a big problem. But if we take a look on the procedure, notice that you rewrite that 1 becomes 3/3, and we get 3 plus 2 becomes 5. So if you think about that, the exponent 5 here can be seen as 3 plus 2. That's how you get that 5, by the way. Okay, visually, it helps us to get that 5. Okay, this is actually true for every fraction that you add 1. Really, believe it or not. All of a sudden, we learn arithmetic in Calc 1. That's strange, huh? Okay, think about this. Pick any number. Negative 27/53. If I add 1, I basically add negative 27 by 53, which is the denominator, right? That's 26/53. Yeah, you try to add that. You get the 26. Okay? Well, anyway, let's go back to our class, our integration. So 3 cancels, so I get negative 1/5, and I will replace my u back to the yellow, 4 minus y cubed to the power of 5/3 plus constant, and that's it. Now, some warning. I see this a lot, even in my Calc 2 classes. Okay, I wonder where they learned that. Okay, square root of a plus b is not equal to square root of a plus square root of b. In fact, this is true for any exponent other than 1. A plus b to the power of n is not equal to a to the n plus b to the n. You know that's true for square, right? This is not a squared plus b squared. Okay, now what I don't want you to do in the next step, you say, oh, this is 4 to the power of 5/3 minus y to the 5th. That's not true. Very common mistake. Okay, but that's really a mistake from your algebraic foundation. Okay, that's not true. Only when the exponent is 1, you can break it that way. And if the exponent is 1, you can just ignore it, right? Okay, but if you have other exponent, no, you cannot split it that way. Okay. It is true for multiplication, but not for addition subtraction. 4y cubed to the power of 5/3 is equal to 4 to the 5/3 times y to the 5th. That's true. Okay. Anyway, let's go on to number 18. I know how to integrate sine, but 1/x in there is the one make it seems to be not doable. Let's call that our u and then differentiate. Oh, that's actually du equals to negative 1/x squared dx. That is our dx over x squared there. Okay, so negative du equals to 1/x squared dx. Now my integral becomes integral sine u times negative du. Actually, integral of negative sine u is cosine u, right? I mean, I can rewrite this as integral of negative sine u, which is cosine u. Then put that u back. Okay. Notice of these 4 examples here, I specifically spend more time in doing my substitution properly. Okay, that's the key. That's the key. So do not rush back to the integration. make sure your substitution is clean, correct. If anything wrong, what you do after that will be not only wrong, but it will be a waste of time. And who knows, because you're missing one r or one variable, the question suddenly becomes, the integration suddenly not doable. Okay, if you think of this integration as a puzzle, it is written in a way that it's already doable. You know it's doable. I mean, the author write it that way, that the author wants that to be doable. Okay, but you need to know how to piece the puzzle together. Okay, I will do more problems, of course. Notice that in the next two questions, I do odd numbers, which is not my habit. I usually not going over odd numbers from our textbook. But if I do, it means these questions are quite special. Okay, not really special, but special enough for me to go over that. Okay, now you see in this number 21, we have x minus 1 over x squared. That looks ugly, but the 1/2 exponent other than 1 is this x squared plus 2 over x to the power of 5. Okay, so I will choose that to be my u. Let me rewrite that as 2x to the negative 1 right away, such that the du becomes 2x minus 2x to the negative 2 in quantity dx. Notice that if I factor the 2, I get x minus 1 over x squared dx, which is the factor of dx we need to tag with to make the substitution completed. Okay, in other words, I will use du over 2 for that x minus 1 over x squared dx. I really hope me color coding it does not confuse you. But make it easier for you to do the reference. Okay, the blue one becomes du over 2. The yellow one becomes u, but I have power of 5. Okay, so I factor that 1/2 out, and integral of u to the 5th is 1/6 u to the 6 plus constant. Simplify a little bit and substitute. Back substitute, we usually call that. Okay, that's for number 21. Number 23, we have this square root. Inside that square root, we have this ugly guy. Okay. 3ax plus bx cubed. If I differentiate, I will get 3a plus 3bx squared dx, which if I factor the 3, when I factor the 3, it looks like a coefficient we have on the top of that fraction tagging with dx. Like, do you see that? Okay, so now my du will be, du over 3 will be that a plus bx squared dx. Integral du over 3, that's my blue part, right? That's my blue part. And then that's 1 over square root of u. Oh, actually, I can just rewrite that as 1/3 integral u to the negative 1/2 du. Thomas, you write it to the right hand side. Well, it's short enough, and then it's just rewriting, right? X, I will integrate. That's 1/3 times 2u to the power of 1/2 plus constant, which is 2 over 3 square root of 3ax plus bx cubed plus constant. Thomas, can I write it as the power of 1/2 instead? Yes, you can. Yes, you can. There is an unwritten rule, I think, by our textbook, just for our textbook. If the power is 1/2 or 1/3 or 1/4, 1/5 like that, then they tend to write it in radical. But if the power is the power of 2/3, 5/3 like this, then they leave it as without radical sign. You know, like this one here, because it's the power of 3/2, then our textbook tend to just keep it this way. Yeah, keep it this way. You know, like the power of 5/2, the power of 3/2. But if it is, we have 1/2 or 1/3, then our textbook tend to write it as a radical, in radical form. But either way is okay. Either way is okay. Now, number 24. This question may be a bit confusing, but it boils down to which integration we can do. Okay? Which one is the derivative of what? Notice that if my u equals to secant x, du is secant x tangent x dx. It's nowhere close to this. If I substitute the secant squared becomes u, then what do I do to the tangent squared? And what do I replace that dx by? Okay, so if one way doesn't work, if one substitution doesn't work, you do another one. Just like in our daily life. I mean, I use this illustration a lot, but you know what I mean, right? If you choose to hang out with one group of people and it doesn't fit you, well, move on, right? Substitute. Okay, find somebody else. Okay, find another group. Okay, in this case, if our u, let me do it sideways. If our u is tangent x, our du happens to work very well. Secant squared x dx. Okay, so is this question hard? It's not hard. It may be confusing because you need to know which function to substitute. Okay, but once you see that, hey, you know what? This is my u. Okay, and then secant squared x dx will be my du. It's straightforward, becomes 1/u squared du, which is integral u to the -2 du, which is -u to the -1 plus constant. That's -1 tangent x plus constant. Or you can say this is negative cotangent x plus constant. Okay? Yeah, so it's really about what function we choose to be our u. And no, it's not something you look at that you know right away unless you have enough experience. That's why I recommend you since the very beginning, if you need to choose a u and turns out to be a wrong substitution, it's still better than you just sitting there thinking and do nothing. Okay? Instead of you keep on thinking and write nothing, why don't you just write something and get stuck so that you know you move on to another substitution. Okay? It's something else. I know this may not be a good advice, but I just use this as an illustration. Okay? If I see a lady that I see to be nice, smart, kind, I want to approach that lady. Okay, instead of like just let that lady dating somebody else, and then I tell myself, if only I try to approach, who knows, I fit with that person. Give it a try, you know. Okay, well, this may not be appropriate illustration, but you know what I mean. It's better than doing nothing, right? Yeah, doing something and wrong and then move on, find a better alternative is better than doing nothing at all. Okay, now in number 26, I would choose this as my u, and you may feel something strange. Let's see if that's my, I mean, it makes sense, right? Inside the square root, and usually that's what we do. If it is inside square root, inside the grouping to the sum power, that's what we do. That's what we substitute. Now the thing is, when I do the du, I get secant square t dt. We don't have that though. Actually, we do. Secant squared is just 1 over cosine squared, which we do have that. We do have that. This guy, oops, wrong color. I usually use blue for my, we do have that. That's our, okay, so this is integral 1 over square root of u du. Okay, so that's integral u to the power of negative 1/2 du, which is 2u to the 1/2 plus constant, and u is 1 plus tangent t. Okay, of course, it's okay for you to write it as 2 square root of, I'm sorry, 2 parentheses 1 plus tangent t to the power of 1/2 plus constant. Okay, that's for number 26. We have a lot more to go, but I hope you bear with me, be patient. And when you practice at home with this video, you may do it this way. You see me doing this, and then you try to do it on your own. You pause the video, you try to do it on your own, and see if you get the same answer, the same steps, similar steps. Doesn't have to be exactly the same. Okay, and follow that principle. The next step should be done in the next line. Okay, this way you can track your own work, right? Okay, and use equal sign if it is really equal. If this is equal to the next line, then you use equal sign. Okay, let's go on. Number 30. Oh, this one is new stuff, because we do replace x, 2 plus x as our du, and du equals to dx, right? So we do have this already. The problem is, what happened with that x squared, Thomas? Seems like we need to do some modification. I'm sorry, this should be u, not du. So I rewrite that u equals to 2 plus x becomes x equals to u minus 2. That's the x that I used to substitute. I'm sorry, I write it wrong. U minus 2 squared. And then I FOIL that u minus 2 being squared. And then I distribute. Okay, in case you wonder, Thomas, how do you do that u minus 2 squared like that? This is just u minus 2 times u minus 2, and then you FOIL that. Okay, or if you happen to memorize the pattern, a minus b squared is a squared minus 2ab plus b squared. Okay, which will give you the same thing we have here. Now then, going back to our integration, I will distribute u to the 1/2. It's u to the 5/2 minus 4u to the 3/2 plus 4u to the 1/2 du. That is 2 over 7u to the 7/2 minus 4 times 2 over 5 u to the 5 half plus 4 times 2 over 3 u to the 3 half. Don't forget plus constant. And then from here, you multiply and substitute. This is 2 over 7. What is my u? 2 plus x. 2 plus x to the power of 7 half minus 8 over 5. 2 plus x to the power of 5 half plus 8 over 3. 2 plus x to the power of 3 half plus constant. I believe our textbook is happy enough for you to go that far. Okay, now in case you want to go a bit further, we can simplify even more than this, but at least I factor u to the power of 2u to the power of 3 half. Then I get 1 over 7u squared minus 4 over 5u plus 4 over 3 plus constant. Then I substitute the u. One over 7, 2 plus x squared minus 4 over 5, 2 plus x plus 4/3. Where inside the bracket, you can actually still distribute this, and combine like terms. It's possible, okay? But at least you know it's doable after we factor out the power of 3 half. Okay, our textbook just want you, I believe our textbook just want you to go as far as what I wrote in purple here. And most instructors do. I myself will be happy enough if you can stop here. You can get this far. Okay, yeah, I give you the blue, the green one because I anticipate you will go far in your calculus, right? Even to differential equation maybe. And in differential equation class, you may need to do it that way. Okay, let me go on. Number 32, x squared plus 1 as our u. So our du is 2x dx. I have one x from that x cubed, but another x squared. You know what? Let me rewrite it first. So this is integral x squared times x dx square root of x squared plus 1. So you see that x cubed there now becomes x squared times x. Now later on, that x dx will tag together, becomes part of our du, right? Du over 2 brx dx. Oh, so what happened to that x squared, Thomas? Well, that x squared, we need to modify it from our u. X squared equals to u minus 1. Okay, now we do substitution, integral of u minus 1, u to the 1 half, du over 2. Take the 1 half out. I distribute u minus 1. I get 1 half times 2 fifths, not 5 half. 2 fifths u to the 5 half minus 2/3 u to the power of 3 half plus constant. Somehow I think we have this question before. Similar one, but where was that? Oh, here. Notice that it's actually very similar to number 8, huh? Very similar to number 8. It just becomes u plus 1 in number 8. In this last question here, it becomes u minus 1. You see that? Okay. I will distribute the 1/2 becomes 1/5 and substitute at the same time. Okay, that will be x squared plus 1 to the 5/2 minus 1/3. I distribute the 1/2, right? And then x squared plus 1 to the power of 3/2 plus constant. That's what it looks like. Now, again, in anticipating that you will go to differential equation, I think I will distribute the 2/15 and u to the power of 3/2. So inside the parentheses, I will get 3u minus 5 plus constant. That will be 1/15 u to the 3/2. But then 3u, when I substitute, notice that we can distribute and simplify further. Again, this is if your instructor wants you to go this far, once you go this far, it means your instructor look up to you that you can go this far. Okay, some algebra part. I'm sorry, I'm not feeling that well. I'm having a cold right now. I hope it doesn't distract you. Okay, in the next couple questions, how many more? 5, 6, 7, and 2-word problems, 3-word problems maybe. Okay, number 38. This time we have definite integral. Okay, remember the rule in my class, when we have definite integral and you do u substitution, beside finding out what the dt become, which we get used to do already, right here, dt becomes du/3. This is my u. This is my dt. But at the same time, I need you to know what happened to the interval of integration. Okay? Substitute that right away. I know different teachers teach differently, but trust me, this will be the most convenient way. U at 1 will be 3 minus 1. That's 2. So my new integration becomes integral from -1 to 2 of u to the 50 du/3. Okay, the key part is you need to change the limit of integration also, because the variable of integration is u. If the variable of integration is u, then the number you write here is in terms of u. U equals to -1, u equals to 3. Just like in the earlier one, this is t equals to 0, t equals to 1. Okay, you cannot say, oh, Thomas, you know what, I will just do it later. I will just keep it t for now, even though my variable of integration is u. No, you cannot. It's not up to you to decide, unfortunately. Okay, if you want to do the indefinite integral first, fine. Do the indefinite integral, but don't put that 0 and 1 if you are working with indefinite integral. You cannot say I'm doing indefinite integral, but I write it as a definite integral. No, you cannot choose. It's not up to you to choose. There's no freedom of choosing your notation here. Okay, no, it's not true. Okay, and I hope your instructor is also disciplined enough to tell you the same thing. Okay. So I show you all the substitution here. You know what? Let me highlight this also. Okay, so I have that 1/3 out. Integral of u to the 50 is 1 over 51 u to the 51. Hey, it's such a big number. I think I would just leave it like that. From -1 to 2, so that's 1 over 153, 2 to the 51, which is a very big number, minus -1 to the 51. I can simplify a little bit. This is 2 to the 51 plus 1. 2 to the 10 is already 1024. 2 to the 20 is 1,048,576. 1,048,576. I think I may be wrong. I might be wrong. Okay, it's such a big number. Okay, 2 cube is already billion. Yeah, so 2 to the 51. I will just leave it like that. Okay, number 40. As you can see, our issue here with the angle, right? We know what is the integral of cosecant squared x dx. That's negative cotangent x plus constant. So if I can make it our x, right, or u in this case, in the name of u substitution, then it becomes integrable, right? So 2 du is to replace dt. Okay. Oh, what happened to the limits of integration? Don't forget that. Don't forget that. Don't forget it. Oops, sorry, wrong color. So u at pi over 3 is 1/2 of pi over 3. That's pi over 6. U at 2 pi over 3 is pi over 3. Okay. Now then, this is equal to integral. That's our green part. This is from pi over 6 to pi over 3 of cosecant squared of u du, 2 du. 2 du. So this is 2 times negative cotangent u from pi over 6 to pi over 3. Negative 2 of cotangent pi over 3 minus cotangent pi over 6. You know what? Let me move a little bit so that I can save a little space. So this becomes negative 2. Oh, yeah, that's right. Cotangent pi over 3 is radical 3 over 3. Cotangent pi over 6 is radical 3 over 1. So that's negative 2 times radical 3 over 3 minus 3 radical 3 over 3. That's negative 2 times negative 2 radical 3 over 3. So that is 4 radical 3 over 3. It's just a bit longer work. It's more about computation for number 40. Number 42. This is so effing ugly. Hold on. We have square root inside square root. So let's get that to be our u. U equals to 2 plus square root of x. When I differentiate, that will be 1/2. This is u plus x to the 1/2, right? So that will be 1/2 x to the negative 1/2 dx, which is 1/2 square root of x dx. Notice that that's what we have here. Okay. In other words, I can now rewrite 2 du as dx over square root of x. Okay. Now, how about the limits of integration? At 1, u at 1 will be 2 plus 1, that's 3. U at 4, that will be 2 plus square root of 4, that's 2. That's 4. Okay. So 1 becomes 3, 4 becomes 4. Okay, so this integral becomes integral from 3 to 4 u times 2 du. Okay. Which is u to the power of 2 from 3 to 4. Is it right? Oh, well, this is integral from 3 to 4 of 2u du. Yeah, 2u is the derivative of u squared, right? So this is 4 squared minus 3 squared, that's equals to 16 minus 9 is 7. Okay, number 43. As much as this seems to be very hard to integrate, it's about this one. Actually, it's not integrable yet for your level. X cubed tangent x is not integrable yet at your level. Okay, but I want to bring your attention to the limits of integration. They are opposite. They are opposite integrals, right? So if the integrand happens to be an odd function, which I think you can see, x cubed is odd, right? Tangent x is odd, right? X to the 4th is even. So this should be an odd function. Okay, so let's do it this way. Let fx equals to that x cubed plus x to the 4th tangent x. I want to show this function is odd. That is to show that f negative x later on equals to negative fx. That's my goal. Okay, I replace all the x by negative x first and simplify. This is negative x cubed plus x to the 4th times negative tangent x. Yeah, tangent is an odd function, right? Notice I can factor the negative and I get x cubed plus x to the 4th tangent x, which is negative of fx. Exactly as we wish that to be, that it is an odd function. Okay, so if you think about this, this is the only time that you can do an integration without actually integrating it. It's a definite integral whose domain of integration is opposite. The domain of integration is an opposite interval. Okay? Now, once you have an odd function as the integrand, then the integral of an odd function over an opposite domain is 0. Of course, you need to make sure that the function is continuous in that interval, though. Okay, in this case, tangent x is continuous in the interval negative pi over 4 to pi over 4, and therefore this is equal to 0. Okay, you will see the same thing with number 48. I think I will not do that anymore, but yes, at least I briefly describe this, that the domain of integration is our opposite from negative pi over 3 to pi over 3, right? X to the fourth, of course, is an even function, but multiplying by an odd function sine x, later on, this becomes 0. But you still need to show. Okay, let me write it in right here. You still need to show explicitly that fx equals to x to the fourth sine x is an odd function. Okay, that is, you need to show that f negative x, gada bum, gada boom, gada bum, gada boom, equals to negative fx. Okay, now your instructor may be easier than that, not that picky, but if you have an instructor like me that, hey, you know what, for every claim you make, you need to come up with a proof of that. It's like talk is cheap, okay, unless you can show that explicitly, okay? Now you can work that out yourself, but number 48 is very similar to number 43. Okay, let's go on. Let me save some space here. Number 50. I choose this question, I think, because it has some strange behavior that we saw that before, I believe, but it gets more complicated because of the definite integral case. So let's say that's our u equals to 1 plus 2x. So du will be 2 dx. Therefore, du over 2 will replace our dx, right? This is our u. But what happened to our x then? And what happened to the limits of integration? So you see that there are 4 things we need to worry about. The number of colors. I hope now you understand why I color that. At the beginning, we have only 2 colors, right? At the beginning, we only have 2 colors. And then in between, we have 3 colors. Okay, when we have definite integral with substitution, we have 3 colors. I use green for the limits of integration. We also call that interval of integrations. But now we have 4 colors. The substitution u, what happened to the dx thingy, okay, what happened to the limits of integration, and what happened if we have left over like the gray color here. So you see, I solve for x, that's u minus 1 over 2. So my new integration will become integral, oops, I don't deal with the green yet. Sorry, I'm rushing. So u at 0 will be 1 plus 0, that's 1. U at 4 will be 1 plus 2 times 4, that's 9. So that's from 1 to 9. The gray part becomes 1/2 u minus 1, that's the gray part, over square root of u du over 2. That's the blue part, and this is the yellow part. This is the green part. I hope by doing so, I color code them, you don't get confused with the color, but you see that every parts of the original integration is now accounted for. No missing component. No missing component. Okay, so this becomes, let me rewrite them first. This 1/2 with another 1/2, I take it out. I take them out. So 1 to the 9, u minus 1 over u to the 1/2 du. So that's 1/4 integral 1 to 9 u to the 1/2 minus u to the -1 du. I think you can just integrate it from there yourself, right? But let me do it together with you. So that's 1/4. The integral becomes 2 over 3 u to the 3/2 minus 2 times u to the 1/2 from 1 to 9. That's 2/3. I do u to the 3/2 first. 9 to the 3/2 minus 1 to the 3/2, which is 1, minus 2 times 9 to the 1/2, which is 3, minus 1 to the 1/2 is just 1. You may do it another way though. You may have done it this way, and that's totally fine. Like you do 2/3, 9 to the 3/2 minus 2 times 9 to the 1/2. That's fine, that's fine. You can also do it that way. You can also do it that way, okay? But I will do it with the purple one, whichever you think is easier, you know. But I want to show you that the method of computation here exists, okay? And this is 1/4 times 2/3 times square root of 9 is 3. 3 cubed is 27. 27 minus 1 minus 2 times 3 minus 1. 2/3 times 26. You know what? Let me just multiply right away. What am I doing? So 26 times 2 is 52 minus 4. Right? 52 divided by 4, that's 13. 13 over 3 minus 1, that's 10 over 3. I hope I don't make any miscomputation. Oh, that's a long one, huh? That's a long one. I'm sorry. Maybe a bad choice of... No, it's a good choice of questions. Okay, just show you that even after all the substitution that you make, you still need to know how to do your arithmetic. Okay, your pre-algebra, let's say, the square root thingy. Okay, that's you're in Calc 1, something we are all proud of, right? But that pride should come with ingredient. Not just like, oh, I passed Calc 1, but I don't know algebra. Nah, that's not right. Okay, number 52. I will use u equals to 1 plus square root of x. I think this question will require some strange manipulation. So this is 1 plus x to the 1/2 du equals to 1/2 x to the -1/2 du. I'm sorry, dx. The thing is, if you notice, I don't, beside dx, I have nothing else. Beside dx, I have nothing else to take. In other words, I need to replace this x to the -1/2 into something else in terms of u. Okay, so 2x to the 1/2 du is dx. but x to the 1/2 is u minus 1. Now we know what to substitute that by. Okay? Let me highlight that here. And the limits of integration from 0 to 1, I think that's on the easier side, is u at 0 is 1, u at 1 is 2. Now the integral becomes integral from 1 to 2. The dx is 2 u minus 1 du over u to the power of 4. Let me show you that everything is already accounted for. Okay? Now, before I go on with this integration, which I believe you can just do it yourself. You can, but I will do it also for you. This is actually 2u to the negative 3 minus 2u to the negative 4 du. Is it right? Or you can factor the 2 out yourself, right? Okay, so this is 2 over negative 2u to the negative 2, and then minus 2 over negative 3u to the negative 3 from 1 to 2 like that. Okay, so this is negative 1 over u squared plus 2 over 3u cubed from 1 to 2. Yeah, you compute yourself, okay? I just leave it there. You compute yourself. What I want to show you is another way to look at this. I think you may have some difficulty here. No, it's actually not that difficult, but let me show you another way to approach this. Slightly different, not totally different. We start with the same substitution, u equals to 1 plus square root of x, right? What we usually do, we differentiate from here, but it's actually doable another way. We can solve for x first. U minus 1 equals to square root of x. So u minus 1 squared equals to x. Then from here we differentiate with respect to, we do differentiation. So 2u minus 1 times the derivative of u minus 1 is 1 equals du equals to dx. Notice that that's our blue color. Do you see that? So instead of me differentiating that first and then do adjustment, I solve for x first. And then I differentiate. Okay? So you see that if I start from here, modified, and then I get the blue one, then all of a sudden, together with the green, then I can go on here. Okay? Now, that's for number 52. Again, I don't show the final computation anymore. You can just do it yourself, I believe, right? Number 55. I usually don't go over this kind of question in class, but I do right now because it's actually an interesting question. Okay? Evaluate this integral by writing it as a sum of two integrations and integrate one of those integrals in terms of area. Let's see. Integral from negative 2 to 2 of x plus 3 square root of 4 minus x squared dx. This is equal to integral -2 to 2 of x times square root of 4 minus x squared dx plus integral -2 to 3 of 3 square root of 4 minus x squared dx. This is a very theoretical question, but there are two observations we do. First one, x square root of 4 minus x is an odd function. F negative x is negative x square root of 4 minus negative x squared. That's negative x square root of 4 minus x squared equals to negative fx. Right? Okay, so fx is odd, and consequently integral from -2 to 2 of x square root of 4 minus x squared dx is equal to 0. Okay, now how about the second term? We talk about this part here. Okay, how about the second integral? Okay, now 3 integral from -2 to 2 square root of 4 minus x squared dx. Okay, let's call that y equals to square root of 4 minus x squared. This is y squared equals to 4 minus x squared plus y squared equals to 4. That is actually a semicircle. Thomas, I thought it's a circle. Semicircle because implicitly from the equation here, y equals to square root something, implicitly y has to be non-negative. Right? So we are actually looking at a semicircle with radius 2, center at origin. Now that integral is equal to 3 times area of semicircle with radius 2. That's 3 times 1/2 pi r squared. Half of a circle, and pi r squared is the area of a full circle. Okay, one of the two cancels, so I get 6 pi. So, going back to the original question, integral from -2 to 2 of x plus 3 square root of 4 minus x squared dx is equals to 6 pi. Okay, now this actually a good question because it combines two important things. First one, that it is an odd function. Actually, the blue one is an even function. It's symmetric with respect to y-axis, right? You can even do it this way. You can even do it this way. You can say this is 2 times integral from 0 to 2 of square root of 4 minus x squared dx, because square root of 4 minus x squared is an even function. You can show that separately, okay? But the key part is the integrand give us a semicircle, or in the last integral here, a quarter circle. This integral here represent a quarter circle with radius 2. Okay, so that will be 6 times par 1/4 of pi r squared. The 2 squared cancel the 1/4, we still get 6 pi. Okay, I hope this question, from this question you see the elegance of how we do the problem using all the theory we have. Okay, last one, number 56. My time's almost up. Evaluate this integral. Oh, that inside I have x to the 4th. But notice I have x here. You know what? I'd write it down first. Integral from 0 to 1, x square root of 1 minus x to the 4th, which I will rewrite as x squared being squared, dx. Now, why I do that? Because remember, if our u is x squared, then the du has something to do with x dx. Okay, so du over 2 is x dx. The limits of integration at 0 becomes 1. Oh, actually, no. At 0 is 0. At 1 is still 1, right? X squared. So this integral becomes integral from 0 to 1 square root of 1 minus u squared du. But this is a quarter circle with radius 1 in the first quadrant. Okay, take a look. Y equals to square root of 1 minus u squared. Implicitly, of course, y has to be non-negative. Y squared equals to 1 minus u squared. U squared plus y squared equals to 1. That's the equation of a circle, right? But the domain of integration is from u equals to 0 to u equals to 1. So we interpret that as area again. This is a quarter of area of a circle with radius 1. Okay, that's for number 56. Number 65, 66, I don't think that's something your instructor will do for you. But I would like to show this. It's actually an elegant, very elegant way to compute integral of cosine squared and integral of sine squared. We don't know the integral yet. In Calc 2, you will see that, even though it's actually not too hard. In trigonometry, we learned the power reduction formula. Cosine squared x is 1 plus cosine 2x over 2, while sine squared x is 1 minus cosine 2x over 2. We can do that, okay? But number 65 together with 66 enable us to do the problem in an elegant way that we don't need to do any substitution at all. I mean, that power reduction at all. Let's do number 65 first. Integral from 0 to pi over 2 of f cosine x dx. We need to prove that this guy equals to that guy. Okay, so if I say u equals to cosine x dx, I'm sorry, d cosine x, then du equals to negative sine x dx. Is that what I want to do? Actually, I don't think that's what I want to do. I'm sorry. No, that's not what I want to do. I want to say that cosine x is actually sine of the complementary angle. Okay, so this is integral from 0 to pi over 2 of f of sine pi over 2 minus x dx. And then when I do substitution, I get du equals to negative dx. So u at 0 is pi over 2. U at pi over 2 is 0. Let me highlight this. This is my substitution. This is my dx. And this is my limits of integration. Okay, so the limits of integration becomes integral from pi over 2 to 0 f of sine u negative du, right, from here. But somewhere in section 4.2 we learn that if I have negative, I can use that to reverse the interval of integration. Okay, because of the dummy variable thingy, this is just, you can replace the u by x and not change. Okay, therefore it is proven. Okay, so it is basically saying that if you have this function of cosine x, and you replace the cosine x by sine x, as long as the interval is from 0 to pi over 2, the first quadrant, then those two integrals are the same. Okay, now in number 66, we have integral from 0 to pi over 2 of cosine squared x. That's the function of cosine x, right? According to number 65, because the interval of integration is from 0 to pi over 2, then I can replace that cosine x by sine squared x. Now, if you don't understand this number 66, don't feel bad. This is actually on the conceptual level, but I want to show you that calculus is supposed to go this far. Okay? Calculus is supposed to go this far. So according to number 65, we already built that a function of cosine x in the first interval have the same integral with a function of sine x in the first quadrant. I'm sorry, not the first interval, first quadrant, from 0 to pi over 2. Okay, now note that integral from 0 to pi over 2 of cosine squared x dx plus integral from 0 to pi over 2 of sine squared x dx, that is equal to integral from 0 to pi over 2 of cosine squared x plus sine squared x dx. Which is equals to 1. Now, integral from 0 to pi over 2 of 1 dx, that's just the length of the interval. Okay, so so the integral of the whole thing here is pi over 2, but at the same time they are equal to each other, right? Okay, consequently, 2 times integral from 0 to pi over 2 of cosine squared x dx, remember they are the same. So I can replace integral sine squared x dx from 0 to pi over 2 just by the first integral, right? This is equal to pi over 2. Therefore, integral from 0 to pi over 2 of cosine squared x dx is pi over 4. Okay, consequently as well, then integral from 0 to pi over 2 of sine square x dx is also pi over 4. Okay, this is where I'm gonna stop. The last two question is, in my opinion, a good one for conceptual understanding. Okay, but the one you really need is everything before this number 55. Okay, let me show you the summary, because I'm gonna post this on YouTube, right? You can stop the video later on and do the screenshot if you like. For number 32, a bit longer. Okay, let me stop the recording at this point.